Welcome to the course on advanced power electronics. So we'll cover case 2 on power quality improvement in multi-pulse converter fed multi-level based induction motor drive. So this medium voltage drive induction motor drive we classified into the different categories. First is types of multi-pulse converter like isolated, non-isolated, and phase staggering, and then the type of multi-level inverter, single DC supply based neutral point clamp, flying capacitor hybrid, and second is the multiple DC based clamping cascaded inverter and hybrid. And the type of motors control like VBIF control, which is open loop, closed loop, or vector control with sensor without sensor, and direct torque control with sensor without sensor. And the type of the modulation techniques like fundamental switching, space factor modulation with phase decomposition, phase opposite decomposition, double phase and a hybrid. And fundamental switching, we divide again switching angle base, which is 3 AEMS, SHE, and hybrid. And second is without switching angle based and LMT and hybrid. This is the classification of multiple AC/DC converter based induction motor drive system. So coming to different configuration for multipulse converter fed this multi-level inverter induction motor drive, and this is typically the first case, the schematic diagram of a 12 pulse AC/DC converter fed 3-level neutral point clamp multi-level induction motor drive with the indirect control. So you can say from input supply, which is given here with a small high pass filter, and then we have a 12 pulse converter with the series connection, which give a typically a midpoint, and then we have a 3-level neutral point inverter with the motor driving, and we have a feedback with the current and as well as the speed sensing, and then we have a control of typically for balancing of the capacitor voltage, as well as we have a control of the speed control here, and with the typically proper factor control diagram. So this is typically again a configuration of again 12 pulse converter and 3-level converter with field weakening. So this is with the direct torque control, that was with the vector control, and here it is the schematic diagram of 36 pulse. You can call it fed 5-level symmetrical CHB based, and in second case it is your 54 pulse 7-level symmetric HB converter to voltage based CHM, and this is schematic diagram of 18 pulse AC/DC fed 7-level binary cascaded inverter based induction motor drive, and the 54 pulse AC/DC fed 15-level binary cascaded inverter fed drive. And this is a schematic of the 18 pulse converter fed 9-level ternary cascaded inverter based induction motor drive, and 36 pulse AC/DC fed 9-level binary CHB converter fed induction motor drive. And this is schematic of 54 pulse AC/DC converter fed 27-level ternary cascaded induction motor drive. This is schematic diagram of 60 pulse AC/DC converter fed direct torque control induction motor drive. This schematic of 20 pulse AC/DC converter fed typically of 3-level, where we convert 3-phase to 5-phase phase shifted, and then midpoint, and then 3-level cascaded inverter with proper sensorless indirect vector control at the diagram given with the level shifted SPM phase factor modulation. This is your schematic diagram 30 pulse AC/DC converter fed cascaded 4-level inverter fed induction motor drive. This is your schematic diagram 40 pulse AC/DC converter fed cascaded 5-level inverter based induction motor drive. So we convert typically, you can call it like how it comes 640 pulse, that we have a typically phase shifted kind of 5-phase converter, and this 60 pulse AC/DC converter cascaded 7-level based. Now coming to design and implementation of multi-pulse converter fed neutral point clamp multi-level inverter fed induction motor drive. So schematic diagram 12 pulse AC/DC with the 3-level converter drive with the, and coming to now calculation of DC link voltage. So for pendulum output waveform, the DC link voltage is calculated VAB max equal to 0.612 MI into n-1 into VDC, where VAB max is the maximum fundamental voltage. You can see voltage, MI is the modulation index, and is the number of levels, and VDC is the DC link voltage. So from the above equation, the DC link voltage is calculated VDC equal to VAB max divided by 0.612 MI n-1, it comes 350 volt. Now coming to design 12 pulse AC/DC converter, in general the minimum phase shift required for cancellation of current harmonics in converter with 6 pulse waveform is given as minimum phase shift is 60 divided number of converters. For this mandatory phase shift for 12 pulse AC converter is 30 degree, that is 60 by 2, and this is achieved by multi-winding transformer which has a delta connected primary winding and its secondary has two isolated star and delta connected winding as shown in the figure. So coming to now design of passive filter. So reactive power absorbed by the transformer is given by Q equal to 7.7 into 10 power into 0.7%, so that comes 540.75 VR. The passive filter required are calculated as the capacitor value CH is calculated as CH equal to Q upon 3V square omega. So putting a value, it comes like a 10 microfarad, and the most dominant harmonic is 11. So inductor value calculated is LH equal to 1 upon omega square CH, so it comes 8.374 millihenry. So resistance of calculated RH equal to X upon QH. Taking quality factor pi, it comes 5.788 ohm. Where quality factor is of high pass filter and it varies from 0.5 to 5 depending on the filter attenuation value, its value is selected. Now coming to control scheme, control of induction motor. So an indirect vector control is used to control the induction motor. So reference speed and sense speed of induction motor are compared and the output of the controller is given as a proportional integral controller. So T reference is equal to T reference n means n minus 1 plus Kp, that is a proportional gain in bracket S E n minus S E minus 1 plus Ki S E n, where Id star equal to I max if omega m less than omega b, and if Id equal to omega b upon omega m max if omega m is greater than omega b. So if Iq equal to 2 by Pm T reference upon Id star Lm into Lr upon Lm, and Vd star equal to Vd n minus 1 plus Kp d in bracket Ed n minus Ed n minus 1 plus Kid Edn, and Vqst star equal to Vq n minus 1 plus equal to Kpq in bracket Eq minus Eqn minus Eqn minus 1 plus Kiq Eq n minus 1. So now the VLST cos theta r equal to VST in minus theta sin r equal to VST, and V beta st equal to sin theta r VST plus cos theta r VQST, and QR equal to integral omega t, that is omega m plus omega SL dt, and that is theta r upon theta r plus theta SL, and SL1 equal to RR upon LR into IPST upon IDST. So the line for sensorless indirect vector, the line voltage VSTB and VSP are sensed, and then phase voltage are estimated. PH equal to 2S VSTB plus VSTB by 3 equal to VS, and VSB equal to minus VSTB plus VS by 3, and VSPC equal to minus VST by 3. Above phase voltage are converted into alpha frame, beta frame. So VAB, VBC, V alpha, V beta, V0 equal to in bracket 2 by 3 minus 1 by 3 minus 1 by 3, 0, 1 by root 3, 1 minus 1 by root 3, and 1 by 3, 1 by 3, 1 by 3, VHA, VHB, VHB, VSC, and the alpha, that is phi alpha and phi beta proportional of stator flux are estimated. Phi alpha is equal to integral of V alpha minus IA RS dt, and V beta is equal to beta minus I beta RS into dt, and that is where the phi alpha r equal to phi alpha s minus I alpha LLS LR upon LM minus LR I alpha, phi beta r equal to phi beta s minus I beta alpha 1s into LR upon LM minus LR IB, and coming to typically phi RST equal to under root phi alpha r plus phi beta, and omega is equal to phi LR d upon dt phi beta r minus phi beta r into d upon dt phi alpha divided by phi r square estimated, and omega SL equal to phi alpha r I beta minus phi beta r I alpha into LMR upon TR divided by phi r st square, and omega st equal to omega s minus omega SL. And this is the space vector modulation technique. So space vector modulation technique for a voltage vectors diagram of three-phase neutral point clamp multi-level flow chart for implementation of SP technique. In the flow chart, find the magnitude and angle of the reference signal from the indirect vector control. So we get the theta reference and we get V reference. So that we and VD, we calculate the calculation of T1, T2, and T0, and form the sectors, and then identify the region, and then we have a input as a sector VD, theta reference, V reference, calculation of dwell time for vertices of triangle, that is TATV TC, and from this TATBC all we select selection of the required phase vector V6 to V26 as it is shown in the diagram, and switching sequence as per the selected voltage vector SA1, SA2, SC1, SB1, SC2, and generation of pendulum signal pulses for all the 12 devices. And then stop. These are hardware photograph, and these are the motor parameters, and these are the experimental results. I mean, you can just see how it is really typically the different your input currents are there, and find out the net. Typically the current are there in the primary and with respect to the supply voltage. Similarly for, I mean, you can call it test result secondary, primary winding currents, and multi-winding transformer input current, filter current, and supply current, and response of this vector in steady state. So you can clearly how the typically your supply current as well as the motor voltage and motor currents are there. So motor current also sinusoidal as well as supply current also close to sinusoidal. And this is the case of dynamics when starting response and response of typically of intermediate signal during starting speed change. So with the speed ID IQ are shown here, and then with the typically your ID IQ during the typically speed changes, and then you can see clearly supply current, supply voltage, supply current, and the motor voltage and motor current. So all are typically the sinusoidal here, even case of during starting. And these are test result for 12 pulse control 3 level total point based vector control induction load characteristic and response for intermittent signal during load change. And these are the typically the power quality of 12 pulse ACT converter at 3 level neutral point clamp based induction motor drive at utility, input voltage and current waveform, power measurement utility, and harmonic spectrum of input voltage, input current. So here you can see that typically the supply current here is 7.3, typically 7.6% with power factor also 0.98. And this is the case when you have a typically the TAD of 4.4% of motor voltage and motor current is 4.4% TAD, motor voltage 29.3%. Typically motor voltage TAD is about 6.2, this 29%. Like in the case of 12 pulse converter 3 level neutral multi-level direct torque control in motor drive, here direct control is used here, and of course for direct control of 3-phase level is pi reference. We have to estimate the flux. Pi reference equals pi rated if omega b, and if pi reference equal to omega b upon omega m, that is pi rated, and that is omega m equal to omega b. So that causes the field beginning, and TST equal to 3 by 2 p by 2 in bracket pi alpha pi I beta minus pi beta s I alpha. So necessary condition for flux hysteresis controller is given as pi equal to 1 if pi st is less than pi reference minus pi delta pi s by 2 pi e minus 1 phi set is greater than pi reference minus pi s by 2. So necessary condition for torque hysteresis control is given as t plus 2 if 2ts, if t error is between 2ts and 3ts, and t equal t plus 1 if t reference t error is between delta t to and t equal to 0 if it is between the minus tb and plus tb, and t equal to minus 1 if 2 minus 2s and 3 minus tb, and t equal to minus 2 when it is between minus 3b and minus 2b. And this is the direct current control 3 level voltage space vector diagram of 3 level neutral point clamp, and this is the simply the selection table of voltage according to the 3 level. So we have a typically all S function with the plus flux level of 2 level. These are the typically a experimental result, test result, winding voltage and current of delta and star primary, supply voltage, current and filter current, and supply voltage current, transformer current and filter current, and the supply voltage current stator voltage. You can clearly see that how the finally the motor currents are sinusoidal as well as the supply current close to sinusoidal. And this is the case like you can see how the pump supply voltage and supply and I alpha IP beta, and the fluxes of stator and flux of rotor are sinusoidal, and you can see stator flux and rotor flux trajectory are showing the complete circle means they are sinusoidal, and the stator current and stator voltage are some sinusoidal, and the angle calculation. And this is the performance during starting where you have a supply voltage, supply current, and motor voltage, motor current, and during speed change also difference how the motor supply voltage, supply current are sinusoidal, and motor voltage also below but close to, and how our motor current are close to sinusoidal. And this is the case when you have a typically the question of during the speed change how the your motor voltage and how the both the flux linkage estimate and flux linkage are shown during starting as well as during steady state operation. These are the performance supply voltage, supply current, and motor voltage, motor current during the typically load change, and then how it is the corresponding flux and torque estimated, and how the typically the here the performance power factor as well. TAD power factor remains 0.98, and the TAD also remain order of TAD of less than 7%, like also. And this is the typically another configuration of 60 pulse ATG for direct torque control induction motor drive. This is the typical design of 60 pulse AC/DC converter with the phasor. The vector diagram proposed multi-phase modular multi-winding transformer voltage vector diagram of transformer T2 and vector diagram of fractional delta connected transformer. So the design of 6 pulse converter. So we say VA1 equal to X1 VA, VB1 K2 V minus K1 VC, and VC1 equal to K4 VB minus K3 VA, and VDC1 equal VD1 equal to K4 VC minus K3 VA equal, and V1 equal to K2 VC minus K1 VB. Here the VA2 equal to K5 VA minus K6 VC, VB equal to X2 VBC, and V3 equal to VC3 equal to K6 VB minus K5 VA, and VD2 equal to K7 VC minus K8 VA, and VE2 equal to K8 VA minus K7 VB, and where NS equal to NDC upon NT, and alpha SCC 360 by N pulse divided by NS, and alpha PRN equal to alpha second upon NT, and NS equal to 6 by 3 2, and alpha second equal to 360 by 10 by 10 18 degree, and alpha PRN equal to 18 by 3, that is 60 degree. So coming to direct torque control 5 level neutral point capacity, the necessary condition for torque stage control is T equal to plus 4 if it is TR is typically less than 4. If T equal to 3, that is it should be between 3 delta TB, TRL should be between 3 and 4 delta TB, and T plus 2 if it is between TRL is between 2 delta TB and 3 delta TB, and T plus 1 equal to delta TB, TRL is between the delta TB and minus plus 2 delta TB is T equal to 0 if minus is between minus TB and TRL is between TB. Well, T equal to minus 1 if the TRL is between the minus 2 EB and minus TB, and T equal to minus 2 minus 3 dB, TR equal to minus T equal to minus 3 when it is between the TR is between minus 4 dB to minus 3 dB, and T equal to minus 4 if TR is your less than minus 2. And this is the typically the your space vector diagram for 5 level neutral point capacitor, and these are the typically you can call it the selection table of voltage vector according to 5 level. So it is a 5 typically error plus and minus, and then you have a 24 switching function correspondingly, and you can select the vector up to going to typically up to 49. And these are the of course experimental result, implement test result of your all the typically the voltage currents, and the primary and secondary voltage and currents, and you can say final currents. You can typically see transformer primary currents and resultant supply current. And so as you can see in the last that the supply current are close almost sinusoidal, and these are typically supply V alpha, V beta, I alpha, beta, and the flux estimation, and the trajectory of stator voltage, stator flux, and rotor flux, which are complete circle when they are sinusoidal, and these are the flux during the steady state. You can see flux are completely sinusoidal, and estimated torque, reference torque, estimated torque, and reference flux and estimated flux during steady state. These are the result for selective vector of VS. So you can just see the supply, motor voltage and motor current, and similarly then supply voltage, supply current, and motor voltage, motor current during typically the starting, and then you can just see how typically your flux estimated, typically corresponding to that vectors. Like this is the test result for when speed is changed, and during that supply voltage, supply current, and motor voltage, motor current, they are very close to sinusoidal, and when the load is changed. And these are the of course the performance like motor supply voltage, supply current, and motor voltage, motor current, and the typically the TAD are typically of your supply current are around 4.5, 4.6, and your typically the power factor is almost 0.99 with the supply TAD around 2%. So here the limitations are neutral point capacitor multi-level requires a more number of the power semi-regulation, and the neutral point multi-level are quite complex for higher number of levels, and NPC multi-level are operated at higher switching frequency, and therefore they have a considerable amount of switching losses. In case of medium voltage and medium power applications, the multi-level inverter, which consists of series power conversion cells, are more suitable for, and then voltage and power level may be released. Therefore, scaling of power or voltage level in installed plant of NPC may be based on quite different. Now coming to modular multi-pulse converter fed symmetrical cascaded ISB inverter based induction motor die. So this is schematic diagram of 36 pulse HDC converter fed 5 level symmetrical cascaded inverter fed induction motor die. So coming to calculation of DC link voltage, so for field output, the DC link voltage calculated VDC equal to VMAP divided by 0.612 MN minus 1. It comes to 184.3 volt, and therefore VDC equal to 185 is taken here to drive a 7.5 kilowatt induction motor from a 5 level symmetrical cascaded bridge inverter. Coming to design of 36 pulse AC/DC, the primary and secondary phase shift of 36 pulse AC/DC calculated, and is equal to 6 by 2, that is 3 degree, alpha secondary 360 by 6 by 3, 20 degree, and alpha by PRN 20 by 2, that is 10 degree. From above mathematics equation, prove that the 36 pulse AC/DC converter, the primary and secondary phase shift should be equal to plus minus 10 and plus minus 20 and 0 degree. So relation between DC output voltage and line voltage of 6 pulse AC/DC converter, VLL equal to 5 VDC upon 3 root 2, and that is VLL equal to 5 into 185 divided by 3 into root 2, that is 137 volt. And the relation between the small winding and large winding and line voltage is typically connected to VLL upon 120 equal to VNS upon sine alpha secondary equal to VNL upon sine 60 minus P secondary, and so VNS equal to sine 120 upon 120 into VLL, that is 54.11 volt, and VNL equal to sine 40 upon sine 120, that is VLL equal to 101.7 volt, and these are typically the schematic and voltage phasor diagram of the delta polygon connected transformer. So the relation between the small winding and large winding and phase voltage of the extended delta transformer is calculated 1 upon sine 160 equal to NP1 upon sine 10. So NP1 equal to sine 10 upon sine 6, that is 0.577. NP2 is root 3 NP1, that is 0.8794. So VP1 equal to NP1 VPN, that is 0.5077 into 39.6, that is 121.645 volt, and VPN2 equal to NP2 divided by VPN, that put the value to 110.704 volt. And these are the typically the, you can call it the implementation of third harmonic injection based space vector modulation, generation of final modulating signal, comparison of modulating and carrier signal, and flowchart for third harmonic injection technique. Like, so here with the flowchart, you define the function and then you add the third harmonics AM by 6 3 omega t, and then compare the magnitude and reference, add the output of all comparator L equal to C1 plus C2 plus 3 C4. If L equal to 4 years, then go to level 2, then if L equal to 3, go to level 1, select this, and if L equal to 3, select 0, and if L equal to 1, then select -1, and if L equal to 0, then select level -2. And these are the typically the test result of primary and secondary winding of transformer T1. So you can add the typically of the 3 transformer primary and then primary currents as a sum of which is very close to sinusoidal, and primary and secondary current of similarly of T2. I mean that's also come to sinusoidal, and then the sum of the primaries, both the transformer combined together, you can see supply current IS is close to sinusoidal. Then you can see the modulating signal, the voltage across the line voltage across the motor, which is also very close to the sinusoidal. And this is typically the your test result for starter line voltage and typically 3-phase starter line and the motor winding current, and typically starting response where you have a motor voltage, motor current, supply voltage, supply current, and motor voltage, motor current, and the response of intermediate signal. Typically you have a reference speed, then your estimated speed, and your D axis and Q axis current during typically starting. And these are the when this supply voltage, supply current, and motor voltage, motor current during speed change, and this supply voltage, supply current, and motor voltage and motor current during the load change, and the intermediate signal supply voltage and speed, reference speed, and the sense speed, and the D and Q current of the control, and your reference torque, then speed, and the D and the Q axis currents. And these are the, of course, you can say the total harmonic distortion of the supply voltage 1.8%, supply current is only 3.5% as the power quality, and power factor is just unity. And this is the case when you have a calculated 5 level symmetrical with the your left part. So you have it even the restored over 8.6% TAD of the motor voltage and motor current TAD 2.6%. And this is another configuration, the schematic diagram 54 pulse AC series converter per 7 level symmetrical converter. So how the 54 pulse converter is realized, you can see the diagram. We have a phase shift in the primary as well as in the secondary, and with the multi-module in 7 level for each phase. So now coming to calculation of DC link voltage. So for staircase modulation, the DC link voltage calculated MI equal to VA divided by E for VDC by pi, where MI, VO, E and VDC represent modulation index, peak of fundamental phase voltage, number of positive level and DC link voltage respectively. From our equation, VO1 equal to MI into 4 VDC upon pi, it comes 2.67 for VDC, and the RMS voltage of fundamental comes VO1 divided by root 2, so it's coming 1.89 1 VDC. So coming to DC link voltage, in case of MLI index motor, the inverter fundamental phase voltage will be equal to the motor phase voltage. So that is VO1 equal to 1 VDC. This is equal to 239.6, and from which we come VDC equal to 126.71 volt. Therefore, the DC link voltage of each power module is taken as a 126.7 volt to drive the an induction motor from 7 level symmetrical cascaded edge bridge inverter. Now coming to design of 54 pulse AC/DC converter. The primary and secondary phase for 36 pulse AC/DC converter is calculated. N is equal to 9 by 3, 3 equal to 3, and alpha secondary 3 is 6 by 3, that is 20 degree, and alpha VRN equal to 20 degree by 3, that is 6.7 degree. And from our equation, the primary and secondary winding phase shift for 56 pulse AC/DC converter is calculated. And these are control of 7 level symmetrical edge bridge. So you can clearly see from neighborhood the implementation of modify selective harmonic elimination for 7 level symmetrical cascaded edge bridge inverter, and reference and phase voltage reference, and flowchart for modify with the equal sharing strategy. So that you can see the flowchart how it is angles are calculated and how it is really coded to calculate 9 angles, and then calculation K1 to K12 and compare the magnitude and then go to different levels. And these are the typically the switching table combination for 7 level inverter for your flag combination F equal to 1, 2, 3, and then the level number of levels to correspond to switching line. And these are the typically after implementation experimental result. So you can see the different voltage, pole voltage, and finally VAO voltage, and then typically the primary current and the all 3 primary current, and then the net current of supply current, which is exactly sinusoidal typical, and typically the different current to primary current and the second primary current, and finally second primary current, and then we have a reference and stator voltage, which is exactly the sinusoidal. And these are typically supply current, typically the voltage and 3-phase voltages of motor and stator current, and your supply voltage, supply current, and the stator voltage and stator current, you see all the way from our sinusoidal. And during starting also supply voltage, supply current, and the motor voltage, motor current, and then the intermediate signal like reference speed, the sense speed, and the D and X current during starting. And this is the case when speed is changed, the supply voltage, supply current, and motor voltage, motor current. And similarly for the case of your load change, when supply voltage, supply current, and motor voltage, motor current, and your intermediate signals reference speed and sense speed, and then your DQ axis current in vector control mode. And this is the typically 3-phase supply voltage, supply current, and motor voltage, motor current, which have a quite low TAD. Like order of power factor is close to 198, and TAD is order of 3.19%. So supply TAD current is 2.14, and motor TAD current is 3.14. And this is typically the performance of list of harmonics, other harmonics in the your supply as well as the motor side current. So coming to the limitation, a 5-level symmetrical CHB converter has been offered a high switching frequency, therefore it has a considerable amount of switch level. Symmetrical CHB converter need more number of switches to achieve. A 7-level symmetrical CHB converter has been operated in, therefore its output voltage have a lower order harmonic, and due to which the torque is more. Now coming to multi-phase multipulse converter fed cascaded 3 and 4 level inverter fed drive. So you can just see here a schematic of 20 pulse AC cascaded 3 level. So you have a typically 20 pulse, 10 pulse each with the cascading, you get the, and then you have a cascaded 3-level inverter with, of course, the vector control diagram with the level shifted space vector modulation. And this is the design of typically 20 pulse converter phase vector diagram, but multiplied 20 medium volt, the multi-winding transformer for medium. So here VA1 equal to X1 VA, VB1 K2 VB minus K1 VC, VC1 VC1 equal to K4 VB minus K3 VA, and VD1 equal to K4 VC minus K3 VA, and V1 equal to K2 VC minus K1 VB. Similarly, VA2 equal to K5 VA minus K6 VC, and VB2 X2 VBC, V3 VC2 equal to K6 VB and minus K5 VA, and VD2 equal to K7 VC minus K8 VA, and VE2 equal to K8 VA minus K7 VB. And this is typically the control of cascaded 3-level inverter to compare the magnitude of reference and carrier signal at the output. And if add 1 to level 1, then if add 1, then level 0, and then level -1. Typically flowchart for your phase shifted modulation based space vector modulation technique. And after implementing, these are the test result of secondary volt, typically the secondary winding voltage of first set and secondary winding voltage of the second set in the second diagram, and then the phase and line voltage of the cascade 3-level inverter, and typically finally the supply voltage, steady state response, supply voltage, supply current, motor voltage, motor current, the last diagram. Like there are the typically VL motors, V alpha beta and E alpha beta of the motor, and then the estimated flux phi alpha phi beta, and then you can see stator flux trajectory which are exactly circle. It means these signal are sinusoidal, and you can see the stator flux phi alpha s, phi beta s, and phi alpha r, phi beta r, and the motor stator voltage and your reference voltage. And these are typically the starting performance. So supply voltage, supply current, motor voltage, motor current, and for speed change, reference change for supply voltage, supply current, and motor voltage, motor current, and then the intermediate circular reference speed and sense speed, then D and Q axis current of the vector control drive. Similarly, for the typically for the second case of speed change, first starting, then second speed change. And this is the case when load is changed, the supply voltage, supply current, and motor voltage, motor current, and typically the power factor 0.98, and with the quite low TID of supply current of 4.4%, and your motor, and typically the TID of motor side is also motor side current is also quite low. So this is the case schematic of 30 pulse AC pad cascaded 4-level inverter pad increment drive with the typically the indirect vector control and space vector, typically modify space vector modulation. And these are the typically phasor diagram for design of 30 pulse AC DC converter, volt diagram, vector diagram, multi-phase multi-winding transformer, and vector diagram of transformer T2, and phase diagram and vector diagram T3. These are the design of 30 pulse AC DC converter. VA1 equal to K1 VA, VB1 N2 VB minus N1 VC, VC1 equal to N4 VB minus N3 VA, and similarly VD1 equal to N4 VC minus N3 VA, and V1 equal to N2 VC minus N1 VB, and VA1 equal to N5 VA minus N6 VB, and VB2 equal to minus K2 VC, VC3 equal to N5 VB minus N6 VA, and VD2 equal to N8 VC minus N7 VA, and V2 equal to N8 VC minus N7 VB, and VA3 equal to N9 VA minus N10 VC, and VB3 equal to N12 VB minus N1, N11 VC, and VC3 equal to N12 equal to VB minus N11 VA, and VD3 equal to NB VC minus N10 VA, and V3 equal to minus K VB. And this is the control of cascaded inverter with the control of modified space vector modulation and flowchart for proposed third harmonic injection to carrier. So you can say a new kind of carrier wave is generated for switching of the devices, and this is the flowchart for that. And these are the experimental results. So you can clearly see the 5 phase winding voltage and their respective currents of transformer T2, T1, and the steady state performance of induction motor drive in the second, where we have supply voltage, supply current, and motor voltage and motor current. And then we have a primary currents of transformer, and then the supply current, and then we have a pendulum voltage and reference signal. And these are the 3-phase pendulum voltage and stator voltage, and then the 3-phase line voltage with the stator current, and then the performance during starting with supply voltage, supply current, and stator voltage, stator current, and the reference speed then the sense speed and DQ access current in vector control mode. These are the case during when speed is changed, supply voltage, supply current, and stator voltage, stator current, and that is for load change for supply voltage, supply current, stator voltage, stator current. And in the typically we have a reference speed and sense speed. We have a D axis, Q axis current for vector current to correspond to vector. Similarly for the D also we have a reference. We have a actual speed and reference torque, and D and Q axis current in vector control mode. And these are typically the result with supply voltage, supply current, and motor voltage, motor current, and their respective harmonic spectrum. So we can see the TAD of motor current is supply current is 3.6%, and motor current is 4.7%. Now coming to multi-pulse AC/DC converter, single unit of multi-winding transformer, and stair type floating point DC converter fed medium voltage induction motor type. So this is the configuration of 18 pulse of 4 level, 10 4 level, and then the typical configuration of multi-pulse, and then the configuration of this a comparison. So 18 pulse 4 level, and then 18 pulse 4 level flying typically, and then the 30 pulse typically 6 level. So this is typically the first operation of 4 level ST mode, A mode, 1 mode, 2 mode, 3 mode, 4, how the switching take place, and then the second configuration, how the typically your switching combination there for different output voltage of your 0 volt VDC, 2 VDC, 3 VDC, and then the operating mode of your typically of 6 level multi-level converter with the different mode output voltage of A phase equal to 0 VDC, 2 VDC, 3 VDC, and 4 VDC, and 5 VDC. And then this is the design of 18 pulse AC/DC converter for primary is your delta, and secondary is phase shifted -20 degree original. So here we calculate theta secondary 365 M pulse divided by MS, that is come 20 degree, and secondary winding calculation VMT equal to 0.612 into S1 minus M into VDC, and from which we calculate the VDC for given voltage. This comes 2430, and VLL equal to 0.2 VDC, so it comes 1791.6 for delta winding, and VLL comes in 120, it comes typically we get the VLN. And the design calculation for the diagram, we get the VNS equal to 707 volt from this. And this is the design of 36 pulse AC/DC converter with delta and extended delta. So you can see the diagram, primary is this, but secondary is delta and extended delta. So from where we get MST equal to 5, and we calculate UST, so from which we get UDC equal to 1375 volt, and line voltage is 1018 volt, and the eta we calculate beta 124 degree. So all the calculation of transformer design is done for the voltage and transfer corresponding to here. And this is the indirect vector control, that from speed sensor we have a reference speed, we have a feedback, we have a reference speed, then we put PI controller that give a reference torque, and from reference torque we calculate the IDM. From an IDM we calculate the IQM, torque producing component. We compare with the torque producing component, we get the VQM, and similarly from this speed we get the flux, and from flux we get the IDM star, and from IDM we put PI control, we get BTM, and from this we calculate the 3-phase voltage for PWM generation, and of course from this we calculate the slip speed for vector control diagram, and then you can see we get the angle, flux angle corresponding to that, so indirect voltage control. And after implementing, these are the transformer secondary winding currents, transformer secondary winding and primary winding currents, and then the reference voltage, motor voltage, and the speed and intermediate signal all are shown here, typically the 3-phase voltage. And here you can say for restarting, the reference speed, the sense speed, the D and Q typically current, and the motor voltage, motor current, supply voltage, supply current, and motor voltage, motor current. And then this is typically steady state, then during starting, and then we have a load change conditions like the stator voltage, supply voltage, supply current, and motor voltage, motor current. And these are the typically the supply voltage, supply current, and motor voltage, motor current, and they are corresponding to the typically the efficiency calculation as well as the total ohmic ratio. So supply current TAD is around 5%, and your you can call it stator current TAD around typically even 4%, like, and it is given here in the detail for the different load conditions when load is varied, how the TAD, motor voltage, motor current, supply voltage, motor current, and motor voltage are given there. And this is the tip configuration multi-level converter with this different type configuration, 18 pulse, 18 different type of inverter. How the TAD are there less than 5% of typically of the grid current as well as the supply motor current also and motor voltage. And now coming to typically the multiple AC/DC converter with multi units of multi-winding arm and stairs type of DC/AC converter paired multi medium voltage index motor drive. So this is the configuration for 24 pulse and 36 pulse as far as converter, and then the how the typically the design of transformer is there. So this is the case of 24 pulse 5 level multi-level inverter, and then 36 pulse converter with the 7 level multiple converter. So these are typically the, you can call it operation of 7 level inverter, how these are the different switching and more the all 5 modes switching, I mean in the 5 level. This is a case of design of 36 pulse AC/DC converter for the design phase shifting with the angle calculation theta prime equal to theta secondary 30 by 3, that 10 degree, and theta secondary 36 multiple. So we have here the primary delta action and the secondary action star and action delta, and secondary your star delta for corresponding. And these are the typically experiments applied here the multi-level inverter response. So there is a phase and line voltage and modulating signal and stator voltage. So you can just see here the current in 12 pulse converter and with the supply voltage, and then the 24 pulse grid current and the typically 3 phase voltage and the line voltage. So then you have how the line voltage is quite clean there and speed, and this is the starting response. So you can say motor voltage, supply voltage, supply current, motor voltage, motor current, and typically the during the your load chain, I mean 0 to 50% supply voltage, supply current, and motor voltage, motor current in the last, and then intermediate signal. These are the typical case of your grid current and the motor voltage, grid voltage and grid current, and motor voltage and motor current, and which have a quite typically a good TAD of the current is around 5%, and motor current TAD is around 4%. Like, and these are the, of course the again the 12 pulse T1 current, the supply current and supply voltage, and then the 3 phase 3 currents and final supply current, and typically the field on pole voltages, and then the line voltage across the motor, like 36 volts current, general current. So here you can see during starting the supply voltage, supply current, and motor voltage, motor current, and typically the here the even the during the steady state how the motor voltage, motor current, supply voltage, supply current, motor voltage, motor current during the starting and different dynamics. And then you can see the state under steady state full load, you have a grid voltage, grid current, and so motor voltage, motor current, which have a TAD of supply current, grid current TAD around 3%, and the motor current TAD 3.8% order. So, and these are typically configuration of your 24 pulse and 36 pulse, and with the which have a grid current TAD of around 3.4%, 4.7, and 4.7, 3.4%. Now coming to multi-pulse AC/DC converter with multi units of multi-winding and cascade based DC/AC converter paired multi voltage type. So here we have 36 pulse converter and 54 pulse converter, and then the different multi-level 7 level, corresponding 5 level, 7 level, and 13 level converter. So these are 36 pulse and 5 level, and these 36 7 level, 36 13 54 pulse 13 level converter. So coming to design 54 pulse converter, you can see how it is. I mean the 3 transformer of your 18 pulse, which are equivalent to giving finally with the power phase shift of primary, it will give you like a 54 pulse design, like 3 transformer. So this is corresponding to how the different angles are calculated corresponding to, and then primarily the angle between them 50 comes to equivalent to 54 pulse converter design. So now coming to DC link voltage for asymmetrical, I mean from MI equal to PL, so it comes the VDC equal to, you put as motor voltage, so it comes your 475 volt, and similarly you calculate the adjustment angle between the two, so it comes your theta prime equal to 20 by 3 6.6, and then 20 degree of the second is 360 by 6 by 3, and then you have a primary winding voltage calculation, NP1, PP1, then VP1 31937 volt, and P2, I mean, and finally the VP2, that's a 5530, and similarly for your secondary winding voltage of PLL 352, and then delta winding LL VP 352 and delta volcan calculation, that comes the VNL equal to short winding long winding 261 and short winding comes to 139.06 with the phase diagram. and these are the typically the modulation technique is used for 5 level typically, and how the typically the your output voltage corresponding to the different PWM technique used. And these are the experimental results, so you can just see clearly the different waveform of 12 pulse kind of converter, and finally the 36 pulse converter supply current on the right side, and then the typically the pole voltage, and then finally the line voltage, which is very close to the sinusoidal in this case of your 5 level converter. And these are the performance with 36 pulse AC/DC converter and 5 level cascaded converter. So during a starting, supply voltage, supply current, and motor voltage, motor current, and typically in the your load change also supply voltage, supply current, and motor voltage, motor current, and intermediate change. And the TAD of supply current is order of, in case of 36 pulse converter, around 4%, and the for the typically 5 level the current TAD is around 4.6%. Like, and these are of course clearly the some result that how it is 36 pulse supply current TAD 3.9%, and 36 pulse in 54 pulse 3.2%, and the 5 level it is current TAD of stator is 4.6, and typically for 7 level is 33.9%, and 36 typically in your 13 level it is voltage TAD 5.2 and current TAD 3.98%. Now coming to multi-pulse AC/DC converter with multi-phase conversion based multi-winding transformer and step type floating type DC/AC converter with medium voltage induction motor die. So here it is a 36 pulse, 30 pulse and 30 with the 4 level and 6 level, 50 pulse 6 level converter. And this is the design of typically 30 pulse AC/DC converter with the 4 level inverter, and 50 pulse with the 6 level multi-level inverter. And this is the case of your third configuration 6 level multi, and first configuration 4 level multi switch the modulation with 0 output voltage, pole voltage, VDC, then 2 VDC, 3 VDC. And then the typically the design of 30 pulse converter with the multi-phase configuration. So you can clearly see how the calculation for the different transformers are made here with the different turns ratio, with the theta secondary typically coming to 12 degree, and the your winding sections are designed typically corresponding to these functions. So these are the typically vector diagrams of 30 pulse multiplier. So you can see clearly here the different winding currents, and finally the supply current of the input, and the phasor diagram corresponding. And this is the typically starting from supply voltage, supply current, which looks to be very close to Samsung, and supply motor voltage and motor current. And during the typically your load perturbation and speed perturbation, how the performance is there, supply voltage, supply current, and motor voltage, motor current. And these are of course the steady states supply voltage, supply current, motor voltage, motor current, which have a typically TAD of supply current around 3.9%, and the motor TAD is around 6%, like also. So here is the summary with the 30 pulse converter, supply current TAD 3.9%, with the 4 level stator current TAD 4.9%, and 30 pulse and 4 level is a 3.7% TAD of supply current, with the motor winding current 4% TAD, and 50 pulse converter have a supply current TAD 3.2%, and the motor 5 level 6 level converter have a stator current TAD of 3.8%. Now coming to your multiple AC signal with the single unit multi-winding transformers, vertical reduced type AC signal. So here we consider 36 pulse with the 5 level, and 36 5 level, and 54 pulse 7 level converter with the proper design. And these are 36 pulse converter with 5 level, and this is another 36 pulse with another 5 level, and this is typically 54 pulse 7 level converter with a proper winding diagram. So here it is indirect vector control, we already discussed a lot, and switching frequency optimized nearest level implementation. So here it is the operational board of 7 level. You can see 0 VDC, 2 VDC, 3 VDC, and minus VDC, minus 2 VDC, and 3 VDC, how the switching take place in your A to G combination. And then typically your supply typically transformer winding currents, and finally the supply current of 54 pulse AC/DC converter. With the adding the 318 pulse, how it comes exactly close to sinusoidal. And this is the typically the winding currents, and finally the coming to the your 7 level converter voltage, and this is the performance during starting. So supply voltage, supply current, motor voltage, motor current, and during startup, and then during the load change you can see supply voltage, supply current, and which have a typically the TAD quite low. So its TID of supply current is order of 3.5%, and the motor TID around 4.7%. As you can see, the supply voltage, supply current, motor voltage, motor current. And of course, it's a summary that with the 36 pulse supply current TID 10.9%, and typically 5 level inverter have a current stator current TID 4.6%, and 36 pulse converter have 3.6 for supply current, and typically the 5 level inverter 3.9, and 54 pulse converter have a 3.5% grid current TID, and 7 level inverter have a 3.7 stator current TID. Now coming to design implementation of multi pulse AC with the single unit and multi-unit multi-winding transformer. So here we are taking 54 pulse with a 9 level inverter and 54 pulse converter and 11 level converter. This is 54 pulse 9 level converter, how it is there, and it is 54 pulse 11 level converters for motor side, and these are the switching states for A to K for inverter, and then the area equivalent modulation technique for 9 level converter. So you can see how the angles are calculated and the flowchart correspond to implementation. And these are of course the typically the all calculation of the angle. So, and these are typically you can see the performance how the 18 pulse current of T1, T2 and T3, and finally the 54 pulse converter current comes into addition of all. Then the motor side, inverter side voltage finally, and the typically correspond to this 11 level pole converter. This is the starting performance. So it's supply voltage, supply current, and motor voltage, motor current, and typically the your torque, speed torque, and due access current, and the load is typically the change how the supply voltage, supply current, and motor voltage, motor current are changed. And here the TID, of course, you can say supply current TID out of 4.5%, 4.6%, and typically the TID of your you can call it your motor TID around again 5% out of that. And here the summary then TID of supply current for 54 was 3.6%, 9 level inverter have again 3.9 on motor side, and 54 volt converter have supply side 4.5, and the 11 level inverter have a 4.57% TID of motor current. Now coming to typical design implementation of multi converter for single unit multi unit hybrid converter. So we take here 24 pulse with 5 level and 30 pulse with the 6 level, and 54 pulse 7 level converter as it is shown here, and 60 pulse with the 7 level configuration. So this is 24 pulse with 5 level, 30 level 6 level, and 60 pulse 7 level converter, and the 54 pulse 7 level converter. And these are typically the 5 level operation of 5 level hybrid multi level and 6 level hybrid one, and 7 level hybrid edge bridge. And these are typically 24 pulse converter design we already discussed many times, and the primary winding design and the corresponding voltage calculation. These are 30 pulse secondary transformer design for phase shift of 20 degree, and the calculation of all voltage calculation for this, and then direct vector control as well as switching pulse optimum generation, and the calculation of the angles for the switching of this. So all the angles finally calculated beta 1, beta 2, beta 3, optimize angle calculation for 7 level. And these are of course the typically simulated result how the voltage of supply stator voltage comes finally, and typically on the right side you can see supply voltage, supply current, and stator voltage, stator current, which are close to sinusoidal, and the performance during typically the at different operations, load change, speed change, and then starting typically, and the TID of the different like a single current TID 3.9%, motor current TID is of 2.48%. This is the case of your 30 pulse 6 level converter. So you can see supply voltage, supply current, and the motor voltage, motor current, and then the TID of supply current 2.3%, motor current TID 2%, and the TID of stator voltage of 11.43%. So this is again for 54 7 level converter, supply voltage, supply current. You can clearly see motor voltage, motor current, and the TID of motor current, supply current is 2.44, motor voltage is 9.12, and supply and TID of motor current is 3.45%. And this is the summary giving all with the 24 5 level, supply current TID 3.9, and motor current TID with the 2.48, and 30 pulse 6 level it is 3.4, 3.4 and 2.2, and 54 pulse is 2.4 and 3.4. These are the industrial application corresponding to the transportation, mining, power generation, wastewater, treatment, cement, chemical, iron, steel, and forest product for this multi-level high power multi-level converter. Now coming to the solved problem, numerical problem. So example 1, a 3-phase 2-level bidirectional boost AC/DC converter, voltage source converter through test transferred 30 kilowatt from 240 50 hertz 3-phase AC mains and sensor voltage. The DC voltage is 750 and fifth harmonic current is 2 limited 5% of fundamental. So the displacement factor is corrected to close to unity. Determine the turn size of transformer, the RMS current and fifth harmonic current. You can see the circuit how typically the converter on 2-level converter on motor side. So coming to solution, a 30 kilowatt 440 volt 50 hertz DC battery of 750 DC link of 750 volt for PWM VSI. Modulation index is PB1.612 MI and -1S. So MI is modulation index, PB1 is the fundamental line voltage, and is the number available, S is the step voltage. The RMS voltage of inverter should be equal to line voltage, and from this VAB1, we calculate 0.612 MI and -1S, that is 440 volt, and S equal to typically 440 divided by 0.612 MA into n-1, so it comes putting value 798.84 volt. And to meet the line voltage of 440, the PWM should have peak of 798.84. So from this one can observe the transformer T1 should have a primary winding equal to 750 and secondary winding 794. The transfer of given N1 upon 750, so NIS1 equal to P upon root 3, that is 39.65, and fifth harmonics is 5% of thunder, this is 1.97 ampere. Now coming to example 2, a 3-phase 2-level bidirectional boost AC/DC converter connected to through a star transformer feeds 30 kilowatt from a 250 volt per phase 50 hertz 3-phase AC mains with the sinusoidal wave. The fifth harmonic current limited 5%. The DC link voltage is displacement vector corrective unity. When the value of inductor phase shift of VSC voltage and the 13 level harmonic current in VSC and TAD phase. So value of AC inductor given as nth harmonic current is IN equal to VN upon XN, XL in N square, that is from this XL equal to VN upon I 5N square, so it comes 5.16 ohm, LR equal into omega, so this comes 16.42 millihenry. The voltage drop due to the inductance is your VLF equal to XLX5, so it comes your 203.123, and power transfer is V converter VS square PL square come 320.231 and P equal to 3 VS V converter sin delta upon X. So delta comes here sin inverse P upon 3 6.1. Error, there should be X here. Okay. The value of nth harmonics is V5 equal to V converter 5. So this comes 365 volt, V7 comes V converter by 7, it comes 46.46, 11 comes like your V converter 11 to 29.7, because VN upon V converter upon V13 comes your 225, V17 comes 19%, V19 comes like your 17 volt, and TAD voltage V5 square, V7 square, V11 and V13, V17, V90 square, V converter, the 28.41, 40%. And the nth harmonic current is IN equal to V converter XL upon N square. So I5 is 2.1, I11 0.51, I13 is your 0.7. Similarly, I17 is your 0.218, I19 0.17, 23 this, and I5 square 7 square 11, 13, 15, 19 square divided by S1 square, it comes 41.72%. So coming to a 3-phase 3-level unidirectional boost AC/DC converter feeds a 15 kilowatt at variable frequency AC motor drive at load of 600 volt from a 230 volt 50 hertz 3-phase AC mains and with an sinusoidal voltage. The fifth harmonic current is to be limited 5% of fundamental. The displacement factor close to unity. Determine the DC link voltage, fundamental AC voltage, phase shift in the fundamental component of voltage source converter AC voltage, and the 11th harmonic. So you can see the 3-level 12 pulse 3-level converter for induction motor drive. So given a phase voltage here, VS equal to 50 volt, we can see 50 hertz. So VSC modulation index VAB1 equal to 0.612 and minus VDC. So VAB1 comes say 440, VDC calculated 399.42. So DC link voltage will be 400 to get the 440 line voltage from AC 3-level converter. Value of AC RMS IS1 equal to P root 3. It comes 19.69 ampere. And the voltage drop due to inductance PL equal to XL IS1. So it comes 203. We converter it under VS square PL VS square, so to 325 and P equal to delta equal to 3.47 and fifth harmonic limit of 5%, so IS5 equal to 0.9, I11 to 0.25. So now coming to example 4, a 3-phase 3-level unidirectional boost converter feeds a 15 kilowatt a variable frequency induction motor drive loaded and 254 volt, 3-phase AC means and central voltage. Fifth harmonic is current is 5%, limited to of the fundamental, and the AC displacement of character unity determine the value of AC inductor, the TID of converter, and TID of AC. So the AC inductor is ILF equal to your your reactance upon omega. So this comes 32.82. The value of your converter voltage VN upon V converter. So V5 is 65, 7 is 46 and 23, and then V11, V13 is 29 and 24, and V17, 19, and we convert. So TID V comes adding V5 square, 7 square, 11 square up to 23, and we convert 28.76. And typically the anathermic current IN upon V converter XL and NI square. So I5 is 1.26, I7 typically 0.62, and 11 comes 0.62, 11, 13, 0.81, I17 0.11, I19 0.73. So TID again adding all the I7 by 5 square divided by I7, it comes 7.413%. Coming to example 5, a 3-phase 4-level bidirectional diode clamp boost PF VSC based ACD configured 75 kW at a variable frequency induction motor drive load from 254 per phase 50 Hz 3-phase AC means with a sinusoidal wave voltage. The seventh harmonics current is limited to 3% of fundamental. The converter is operated at fundamental frequencies to conceal the fifth harmonics in converter voltage. The display factor corrected to unit determine the fundamental phase current, 17th harmonic current, and value of inductor. So these are typically the 4-level convert. So coming to the phase voltage 250 over 50 Hz, the value of AC current is IS1 equal to P load 3. It comes 98.43, and seventh harmonic current is typically 3%, so it comes 2.53. And the nth harmonic IN upon VN L square N square. So XL comes for limiting this current, so it comes 1.76, and LF comes your XL upon omega, so it's 5.6 millihenry. So now coming to example 6, a 3-phase 4-level bidirectional clamp voltage source converter feeds a 275 volt kilowatt to variable frequency induction motor drive load 750 volt 254 volt per phase 50 Hz 3-phase AC means with the sinusoidal wave. The seventh harmonic current is limited 3% of fundamental. The converter is operated at fundamental frequency switching to mode cancel fifth harmonics in output. Converter output is our displacement factor corrected to unity, and that determine the value of phase shifted fundamental component of converter AC voltage and supply voltage, TID of converter AC voltage, and TID of AC current. So this is a 3-phase 4-level induction motor drive, and the given grid per phase V S equal to 54, frequency 50 Hz. So voltage drop due to inductance VL equal to XL IS1, come 173.22, and converter voltage calculated V converter VS square V it comes 307.45, and transfer power P equal to 3 VS V converter sin delta upon X, that delta comes 18.67. Value of an harmonics is Vn upon V converter upon A. So V7 is V converter by 7, so it's 43. V11 is V converter upon 11, so 27. V13 V converter upon 13, 23. 17 is V converter upon 17, 18.03. V19 equal to V converter 19, 16.183. V23 is we converter 23, 23, and TID of the voltage adding all the harmonics, it comes 20.67. And now in a harmonic current is IN equal to V converter XN upon N square. So I7 is converter XN 7 square, so it comes 3.57. I11 comes 1.44. IL13 1.03. I17 0.19. I19 0.84. I23 0. So TID adding all the harmonics come 4.14%. Now coming to example 7, a 3-phase 5-level bidirectional diode clamp boost PFC AC converter feeds the 45 kilowatt variable frequency 60 volt from 230 volt 50 Hz 3-phase AC means, and with the sinusoidal wave voltage, the seventh harmonic current to be limited 3% of fundamental AC current, and converter is operated to fundamental frequency switching frequency mode to cancel out fifth harmonic converter output voltage. The displacement factor is corrected close to unity to determine the fundamental phase current, seventh harmonic current, and the value of AC inductor. This is the 3-phase 5-level converter. The given supply voltage is Vs equal to 250 volt, frequency 50. The value of AC RMS current is IS1 equal to PS upon, it comes 59.055 ampere. Seventh harmonic current is 3%, so it comes I7 1.72. So nth harmonic current is IN equal to VN upon XN N square. XL comes 2.93, and LF from this comes here 9.33 millihenry. So example 8, 3-phase 5-level bidirectional diode clamp boost PSC converter feeds a 45 kilowatt from variable frequency at 650 volt from 654 per phase 50 Hz 3-phase AC mains with the transfer voltage. The 7th harmonic current is to be limited 3% of fundamental current. The converter is operated in a fundamental wave switching mode to cancel out 5th harmonics. In converter output is displacement factor correctly close to unit. Determine the value of phase shift in fundamental component of AC voltage and supply voltage. The TAD in converter is AC voltage and TAD of AC current. And this is the 5-level inverter of neutral point induction motor die. So coming to the converter voltage, the voltage drop L equal to XL of IS1, that is 173. The converter is calculated V converter square IL square, so it comes like 307.7. So power transfer is P equal to 3 VS V converter sin delta upon X. So delta comes 11.07, and the value of nth harmonic V converter upon nth. So V7 equal to V converter by 743. V11 comes 27.94. V13 comes 23.64. V11 17 comes V converter of 170 18 volt. V19 comes 16 point and 113 point, and adding all the harmonics in TAD V7 square divided by V converter fundamental square 20.67, and harmonic current nth upon V converter election square. So I7 comes 2.14, I11 0.87, 13 comes 0.6, 17.3, and 19 comes 0.21 and 23.2. So adding all the TAD comes I7 square up to 23 upon IS1 square, it comes 4.14%. Like, so coming to example 9, a 3-phase 5-level unidirectional HDD converter fed variable frequency induction motor drive at the 650 volt from 230 phase 50 Hz 3-phase AC mains with a sinusoidal wave, and the 7th harmonic current is limited 3% of fundamental AC current, and converter is operated at fundamental frequency switching to cancel out 5th harmonic converter in the output, and the displacement factor corrected to unity given the equivalent resistance of load and fundamental current and 7th harmonic and value of index. This is typically your 3-level 5-leg. So coming to grid voltage 254 50 Hz, and the fundamental switching is MA equal to Vn upon 4 S upon 5. So where the MA is equal to modulation, P equals the fundamental, B is the number of positive step, and B is the addition. So comes P fundamental, come B converter MA 4BS, it comes 2.4 VDC and root mean square. The fundamental is Vn1 Vn upon root 2, it comes 1.71 VDC, and the RMS value inverter fundamental equal to the Vn1 equal to 1.7 VDC. So VG comes 254, so VDC comes 148.54. So DC voltage will be 594.16 volt, and DC output is equal to the VDC IDC. So die 200 kilowatt, the equivalent resistance VDC square point will come 17.651 ohm. The fundamental current IS1P root 3 26.63, and 7th harmonics your 3%, so it's 0.79, and nth harmonics IN equal to Vn upon XLN square, which comes 6.51, and 17th harmonics I17 Vn upon this, so it comes 0.1 point, and value of inductor is I1 equal to 20.89 ohm. Coming to example 10, the 3-phase 5-level unidirectional converter with 10 kilowatt to variable frequency AC motor drive at 650 volt from 254 phase 3-phase AC mains and sinusoidal voltage. 7th harmonic current is to be limited 3% fundamental current, and the converter is operated fundamental frequency switching mode to cancel 5th harmonics in converter output is the displacement factor corrected unit determine the value of phase shift in the and supply voltage, TAD of converter voltage, and TAD of AC current, and this is the 3-level 5-level converter. So VL equal to typically XL into IS1 172, and converter voltage V under root VS square VL square, so 306 point, and the P equal to 3 VS B converter to sin delta upon X. Delta comes from here the 4.9, and value of nth harmonic Vn upon converter nth. So V7 comes for 43.84, V11 comes 27, V13 comes 23.6, when 17 18 volt, and 19 16, and 20 third comes 20. So TAD of under root V7 square 2 and 27 upon V converter fundamental 20.64, and nth harmonic current is nth upon V converter electron. So I7 comes 0.94, 11th harmonics I11.93, I13.2, 17 is your 0.61, I19.13, and I23.0. ITAD adding all the harmonic I17, 19, 23 divided by I1, so it comes 4.16. These are the references which are used for developing this material, and thank you.